Has anybody got anything on their mind? Anything we've done? Sounding pretty empty setish. Yeah? No. Alright. Cool. Let's go onward. I think today, oh man, I learned a bunch of cool stuff on Desmos. We'll have to play with. I highly recommend, and it might actually come in handy as you explore some of the stuff we are talking about today. We went crazy on the unit circle last time, didn't we? On Desmos, one of the things you can do is, besides I showed you how we could do vector valued functions, but they have this whole little panel of functions that has a lot of really cool stuff in it that one day I'll explore it more thoroughly. But the function I was looking for is, if you want to define a vector in 2 or 3 space, you could say v1 or whatever. I think it might even turn that into a subscript automatically. It's pretty smart, pretty amazing. You say equals, and then you go here. You can't type the word, which is weird. But if you go here and find down in the vectors function, there's a function called vector. And it requires 2 points. So you put in P1 and P2, separated by commas. I'm having trouble with that. That doesn't bode well. But you enter a vector like that, and it shows it in 3D space, pointed in from to direction. Really cool, really helpful. So and you could put parameters in here, right? You could parameterize this and make the vector move. And I wish I could give assignments like that. I don't know how you'd turn them in. Anybody have any idea how that would work?
You can save Desmos projects.
Yeah.
I think Desmos has a classroom learning tool. I've used it before.
Really?
Where it was kind of like World Class, where you can turn them in and you do them in Desmos.
I've done assignments where I've just saved it and then we submitted the link to you.
Oh.
And you can just open it and play with it yourself.
Oh, okay. I think I might have to create some kind of vector 3D visual. That just sounds freaking awesome.
I'm getting evil ideas now. Okay.
What's that?
I'm getting evil ideas.
Too late. Too late. All right. Today we're going to talk about linearization, so derivatives and integrals with respect to vector valued functions. But I guess there's an even more primal set of properties I just want to at least make sure we're aware of. So if I have a vector valued function R of t and a vector valued function S of t, well, shit, let's hold off because this actually involves the derivative. So let's define the derivative. We'll just start with R of t. So I'm just going to give the definition and then talk about it. And I want to show some different notations. If I want to take the derivative with respect to the input variable t of a vector valued function, essentially what this means, and let's get some definitions here. This is x of t, y of t, z of t. And we'll just do it for 2D, 3D. You can just go remove one of those and all this applies to 2D. Is just take the derivative of the components respectively. And you can look in the book. I don't even think I'm going to prove this because you can look in the book for the proof of it. It essentially comes down to the definition of derivative of a function of one output. So scalar function, f of t, takes real inputs, spits out a single real input, so this is a scalar function. And it might have a more restricted domain here. It looks like any t works, but it might be some collection of points in R. But if I wanted to find the derivative of that at t, we started with this maybe day 1, I think, in the class. I'm going to take the limit as h goes to 0. I'm going to perturb the input by a tiny bit, h, and I'm going to subtract off the original input value, and I'm going to divide by the perturbation. And this limit is the first derivative, and for that we might also use f prime of t, and we might also use a dot of t, like that, just notation. This shouldn't be super surprising. My gosh, I hope not. Yeah, that's Calc 1. So the basic idea here is I want to do that same thing with a vector value function, but here it's a little bit more interesting. Not that it's not interesting. And let's do a vector valued function, r of t, right there, and here's my x, y, and z components. So what I'm doing when I do this is I'm taking r of t at some fixed location. Now that's a, woo, that is, woo. I made some color. Daniel, can you pick me a good color? I still haven't found that indigo. I think somebody snagged it.
That's so sad.
It is sad. Why is the world like that?
The
Why-
indigo.
Why do people steal indigo markers? Looked all around for it. But then again, I like live in such a rat's nest of a life. It could be in that bag, and I just can't see it. So this is for a particular value of t, and then I move t just a little bit, and that's going to change where the vector is pointing. So this would be r at t plus h. Looks here like t is positive given the way it moved. T could also, excuse me, h is positive because I moved forward. H could be negative, and this arrow would point back here. All good. And then Daniel, could I please have one more pen color, please? Totally different. Thank you so much. Oh, that's nice. Yeah, cool. So this R, what we're going to have on top here is the later state of the vector minus the previous state of the vector. And that's actually this vector right here. So that green vector is this tip minus this tip. That is this difference. And we're going to divide that by the change in the input value. So right now, I see that t is a positive quantity, but I'm going to look at this difference as h shrinks to 0, and that is the definition of the first derivative. Looks exactly the same, right? It looks 100% the same, but then we realize, oh, this is components. So when I come in here, I guess I am doing all this. This is x of t plus h, y of t plus h, z of t plus h. It's probably good to do it. Minus, because all this is the xyz function that I've defined at the top, minus x of t, y of t, z of t over h, and using vector properties. This top is just that, it's a new vector, x of t plus h, and I'm gonna actually make this all big because I can do all this stuff. This is a scalar quantity, so it's just a scalar multiple. So it's x of t plus h, x of t subtracted over h, y of t plus h minus y of t over h, and z of t plus h minus z of t over h. And the only thing that might be like kind of sketchy is, can I bring this limit inside and take the limit of this, limit of this, limit of this? And the answer is yes, I can. And when I do that, I get derivative of this, derivative of this, derivative of this. That's enough. Does that make sense? Kind of basic vector properties along with the definition of a scalar function's derivative. Cool. So now I can talk about the little list of critters that I wanted to talk about. And I want a new color. I'll pick this time. Sure seems like I started with a lot of colors, and I don't have many anymore. So now we have vector valued function brick red R of t, brick red S of t, vector valued functions. Let's look at some derivative properties. Derivative of the sum or difference is the sum or difference of the derivatives. Now here I'm going to use two different forms of notation just to practice. So this is going to be r prime of t plus or minus s with the vector hat prime of t. So that prime notation, you just use it on the vector, the function name, just like you would in the scalar case, all good. Putting a dot on top of this gets a little bit much. It's just a lot of stacking. Like I've done it a lot, especially in my notes while I was thinking about what we're gonna talk about, you know, putting a dot up here. Looks cool, kind of gets a little hieroglyphic-y looking. Let's see, so also ddt of a scalar, multiple of one of these functions, the scalar comes out front. And I don't need that anymore. Let's put r prime t. These two properties together, what do we call that? What is the word that talks about how scalars come outside and I'll just tell it. The way I'm asking the question is kind of stupid. This is linearity of the derivative. I think I might have said that a long time ago. I'll bring it up again. The derivative is a linear operator on functions. So just like a matrix is a linear operator on vectors, the derivative is a linear operator on functions. And here your functions are your vectors. But that's starting to get stuff a little strange, so we'll stop talking about it. This is kind of surprising and cool, that if I take the derivative of r of t dotted with s of t, so this is the dot product, right? Because these are vectors, so that is the dot. It works just like the product rule. And you could prove this by going to the definitions, working this all through, but shockingly, this is r prime of t dot s of t plus r of t dot s prime of t. So that's the product rule. For the dot product, works the same. Even more surprisingly, or maybe perhaps equally as surprisingly, if I have the cross product of r of t crossed with cross product of s of t, it works the same way. It's just like the product rule for both. I know, that seems wild. It seems really wild. Now I haven't proved this to myself. I read it in a book. I believed it. But I haven't convinced myself of it, which is not great. R prime of t cross s of t plus r of t cross s prime of t. So no matter what you're doing, dot or cross product, you got the product rule. Pretty cool. And then we don't have like a quotient rule, because what does it mean to divide two vectors? We don't really have anything that makes sense of that operation. So we don't have to worry about weird quotient rules or any of that kind of stuff. Let me check in my notes and see where we're at. Oh yeah, one last one, a chain rule. So the chain rule this is a little bit more complicated than Calc 1 chain rule, but not much. When we get to multivariables, then it's going to become a lot more complicated, but currently not so bad. So the last one is the chain rule. And here I've got the derivative of r of, before I plug t into the function, the vector function r, I run it through another function f. So look at how this is working. I take t, I get out f of t, and then I plug that into r as my input. So I'm tweaking the t before I run it through the r. If I do that and take the derivative, the way this changes is the f prime of t comes out times r prime of f of t. So if you think about that, that's just like the normal chain rule. Derivative of the outside with the inside left alone times the derivative of the inside. Yes, ma'am?
And the f is just going to be a scalar function?
Yes, yes. Let me make that clear. Yeah, Camila, absolutely. So f of t is a scalar function. Absolutely. And the reason we bring this, normally I would put the f prime at the end, but it's a scalar, and we always have scalar times vector, so just to kind of keep with that convention, keep our rhythms in check. So let's actually do some practice here. Now we've got how to do this. We know how to do derivatives. Spent some time this semester doing a little, spent like a whole semester doing it once, 1 billion years ago. So let's actually remind ourselves of some things, and this is one of our important applications. So if r of t equals the position of a particle, Calc 3 exists for one thing. It's to study particle motion in space. This is why we have Calc 3, for fluid dynamics, studying turbulence, studying motion in space of whatever is flying through space. These days, there's a lot of shit flying through space. Position of a particle at time t in 3D space. Let's just say that. Then the velocity of that particle is a vector. So this is the velocity vector at time t. Let's draw a little picture here. So if this is r of t, and you imagine the axes however you want, we're flowing like this. If I'm at some t here, pick a good curvy spot so that the vector, the tangent vector, can depart from the curve in a way that you can draw. So if this is r of t here, then this is v of t, which is r prime of t. So that's just the first derivative, your velocity. And it's equal to the tangent vector to r of t at t, time t. And then one more is the acceleration. We're gonna do a bunch of stuff with this. So the acceleration vector, there's some cool stuff we'll see today. Probably all the physics folks and probably all you science folks know this stuff, but it'll be cool to see it in a different frame of reference with calci focus and a person who barely knows what's happening with physics. So this is the rate of change of the velocity. This is a tangent vector to the velocity curve, but that means it's the second derivative of the position function. So this equals the acceleration vector at time t. And it's hard to say exactly how that would look relative to this. I kind of feel like it's probably, I don't know, physics folks, help me out. It feels like the acceleration vector would kind of be like that because we're curving. But you tell me, it just feels like that, right? Like it's changing the velocity in that direction.
It'd be pointing inward.
Does that sound right?
It's like circular motion, the acceleration always points towards the center of the circle.
That was you told the secret.
Oh,
That's okay, that's all good, yeah, you're right. That's kind of what, no, that's good, it's good, thank you. Yeah, so I'm kind of thinking the acceleration vector might look something like that, kind of pulling toward the inside to arc it around that loop. Yes?
That's equals, right?
That is, good Lord, yes, it is. That is the velocity equals r prime, yes, sir. And then I'll just put it here again, this is r double prime, to make things at least consistent. Cool, so let's do some stuff. Let's compute some of these things. We might as well get to the punchline thing. Maybe we'll pull out Desmos and do some stuff. So, I got RT equals, not too surprising. Of course, that's out again. Find the first two derivatives. In other words, find the velocity vector, find the acceleration vector. And let's look at those in a picture because we know the trajectory is a unit circle. I hope we know that. Where's Mr. Czar? Where is Mr. Czar? You weren't here on Friday, my friend. I think that's true. Yes, I'm talking to you, Mr. Czar. Hope you're not sick. You know, I will give you guys a day off, though. But it'll be a Friday, something good like that.
Into that.
Yeah. It seems like the Friday before spring break might not be that bad.
Yes.
That feels right. Yeah. Slightly longer spring break. Not that anybody else will do that. There's some professors here who wouldn't dream of that. And we don't have to talk about this with other professors, right? We don't have to say, Dr. T is blah, blah, blah. You don't have to say that to anybody. I'd ask that you not.
Just the camera.
Just the camera. Well, nobody who I don't want to hear this ever would watch my videos. So, okay, so we got RFT is the unit circle as we talked about. Here's t equals 0. Let's grab a few moments. The only reason I say this is because I've had people do that before. I've had like Cyber come up to me and say, oh, I heard you canceled class. I'm like, why did you hear that? What business is that of yours? So can somebody help me out here? What's V of t? Alexander, we're chatting. What's the derivative of cosine?
Negative sign.
Yeah, beautiful.
Cosine.
Yeah, that's so good. Thank you. Well done. Thank you. Daniel, what's the next one?
It's negative cosine, and then negative sine.
Cool. Thank you. We all feel good about that? Nice, nice. So, let's take a look at some things here. Actually, let's look at just a really cool fact. Let's take V of t dotted with A of t. Can you please compute that? You might already know the answer, but just compute it anyway. Just see it mathematically. And then we'll understand some cool physics stuff from a math point. Hopefully you're getting 0 out of there. No matter what t is. Let's use a nice mathy symbol. It's the for all. If you're not familiar with that, that is for all or for every. And my math friends, like this is part of our language that we use every day. It is called the universal quantifier, which makes it sound super groovy. How, are we feeling okay about getting 0 out of that dot product? Because I took negative sine of t times negative cosine of t, got positive sine cos, plus cosine of t times negative sine of t gave me negative cosine, and those cancel, and I get 0. What can I conclude about the velocity vector and the acceleration vector?
90 degrees.
What's that?
At a 90 degree.
They're 90 degrees, they're orthogonal. So the dot product is 0, so that tells me that the velocity vector here is orthogonal to the acceleration vector. So let's actually sketch out a few and see what this means, and then kind of talk about physically why this is so. So first off, it wouldn't hurt to get all these vectors at a certain point. Could we all do that together? So let's get R at 0, V at 0, and A at 0. And just look at those vectors. And we already have R at 0, right? It's this guy. It's 1, 0. So that's not super shocking here. Make these in different colors. This shouldn't take too long if we've got the formulas and we know cosine and sine is 0. So I'm gonna put these up. You tell me if we need to talk about that. And of course, I'm happy to talk about it. Bless you. Thanks. These looking okay. Cosine of 0 is 1, sine of 0 is 0. And once we have that, we pretty much own all those vectors right over there. Everybody's good. Just want to make sure it's cool. All right. So here's the position vector. And of course, we just think about the tip of that thing for where the particle is located. We don't always have to, but we mostly will. The velocity vector, you imagine it emanating from the current location. So it's not just, it could be thought of as this, the vector 0, 1 right there, pointing straight up. But we think of it as the vector emanating, so that's V of 0 right there, from the point that we're located, that we're thinking about on the curve. So that is the velocity vector, and notice it itself is orthogonal to the position vector, just because a tangent line to a circle is always perpendicular to a radius on the circle where your tangent. But then this acceleration vector, ooh boy, that doesn't look very straight up and down. I don't like it. That feels better. And it's the same height as 1. And we make that all look like that. The acceleration vector is actually kind of the reverse of this vector, and I also imagine that greeny. The acceleration vector is -1, 0, and so that's acting like this. So that's A of 0. And again, that, as noted, that is orthogonal to the velocity vector. So when you're spinning, imagine you like had a rock on the string and you're spinning it. Somehow you got it going and you're spinning it with very little movement of the central axis. And you're keeping that at a constant speed. The acceleration is, you're not speeding up. So if this thing is at a constant velocity, and so think about how a sling works, right? When you're doing this, and you let go of it, wherever you let go of it, it moves tangentially, like so, right? I let it go about right there, kind of shut up, and I knew that was gonna be okay. But the acceleration, so if this is a constant velocity, what do I mean constant velocity? It looks like it's moving. What do I mean? Do I mean constant velocity?
The magnitude?
The magnitude. So what I really mean is constant speed here. So notice here that the magnitude of the velocity for any t is what? Sine squared plus cosine squared is 1. Square root of that is 1. So this always has a speed of 1. So let's just make a little note here that the magnitude of the velocity is equal to the speed. So I have something here at a constant speed. And when that happens, when I have something at a constant speed moving in this circular pattern, and we're gonna check something out I'm kind of curious about in just a second. The acceleration isn't making it speed up. So if this acceleration vector is in the direction of the velocity, it means you're kind of getting pulled in that direction, that you're accelerating and whatever is happening, whatever force is accelerating you is acting in the direction of the current velocity. If this acceleration vector were acting opposite that, we would be decelerating. So it's pulling against that current velocity vector. But right here, it's completely perpendicular to it, saying that there's no speeding up at all. We're just maintaining a constant velocity all the way around. Seems really weird to me. It's just wild. Does this make sense? I like physics people, chemistry people. Does what I'm saying sound at all like not bullshit? And look, I set the bar really low. Does it sound at all not like complete bullshit? Okay, I'm right. Okay, cool. So I kind of want to check something out here. Let's just see what happens. Let's say I've got the velocity is constant. So that means that the velocity squared is constant. Now, I don't know how this is going to turn out, but I'm kind of like curious about it. So I'm going to use the dot product version of that. So that's v of t dotted with itself, and that's 1. Oh, this is going to work out pretty good. So let's say I've got a particle with constant velocity, no matter what the time is. And this is 1 over here, right? So now I'm going to take the derivative of both sides. So I'm going to take derivative of this side. This is going to work out. And I've never done this, maybe in public or private. What's the derivative of the right-hand side?
0.
0. It's constant, yeah? Derivative of the inside, that's a dot product. I'm going to use that product rule that I had up there a little bit. So that is v prime of t, derivative of that, times that left alone, plus that left alone, which is just v of t, dotted with, and this is dotted with v prime of t. Well, those two are the same, and this is actually the acceleration at time t, right here. So notice that the left-hand side is just 2 times the acceleration vector dotted with the velocity vector, and that's equal to 0. Divide both sides by 2. And it says that if I have a constant speed, my acceleration is always perpendicular to my velocity. That's kind of cool. It's not just in a circle. It's just always that way. And that kind of makes sense. If I've got this particle and it's not speeding up, it's got a certain velocity and it's not moving, then the acceleration can't be pulling forward. It can't be pulling backwards, and so it must just be acting orthogonally to the particle. Kind of makes sense. Makes sense to me. This is a math class, but the only reason this math class exists is because of physics. So we got to talk about it. So this means A of t is perpendicular to V of t when we have constant velocity. Cool, that's neat. Anybody ever seen that before in a physics class or? Yeah, nice. You've heard it, maybe you've heard it. Now you know it, now you believes it. All right, let's see, I got notes somewhere, but I don't know where. Oh, here, thank you, thanks. Let's do, oh, that just sounds boring now. All right, Yeah, let's do 1. Okay, I made this one up. This is a goofy ass problem. But let's do it. So I've got a particle in motion, and we're just gonna do 2D. You want 3D? Add a constant third dimension. You can take it to any slice you want, or put 0, comma 0. But this is a planar action, and all our stuff still works. So I've got a particle whose position at time t is given by, and now here I'm going to use s of t. That's a more classic position vector. It's still the r from before, but I think it's maybe more physicsy. Again, I think I've mentioned that's like probably some weird German word. Negative 4.9, that sounds sus, doesn't it? Plus 8t plus 5. So that's negative 4.9 t squared plus 8t plus 5 is the second component. First component is t. This actually, this might not be that bad to talk about. So here's a quick sketch. If I were to trace that out, let's also assume t is positive. And let's assume up until t greater, less than or equal to t final. And t final is when it hits the ground. And I don't know what that is off the top of my head, because I didn't figure it out. But we could figure it out when we hit the ground. So this is actually just parabolic motion. S of 0 is 0, comma 5. So my initial height here, and I'm going to say meters. I better say meters if my units are going to be true to physics life. So there's 5 meters. That's where I start. And then I go up and I come down. So that's actually t final there. But no, that's not the t axis shit. Sorry, don't make that t. That is x of t. This is y of t. This is x of t. I got a little scary there. It is t, but officially it's x of t, y of t. So this is our particle in motion. Looks like classic parabolic flight kind of stuff. Alexander, is there anything I can help you?
This is a 2-dimensional vector?
Yes, sir.
Okay, that
Yes,
makes more
yes.
sense.
So could you please find the velocity vector and the acceleration vector? Nice little power rule exercise. And then see if it makes sense, especially if you have some physics background. I'll start working on T final. square root of 162 for me, please? Somehow.
Just need that number, and with like 1 decimal point would be great.
12.7.
12.7, awesome. So Alexander, while you have that out, please. Oh, sorry.
So I'm gonna take the plus, because the minus doesn't make sense. The minus is where it would hit if that parabola kept going into negative time. Then I would have a negative answer here, but I'm gonna take the plus answer, so would you please? Yeah, you got this?
Yeah.
Cool, awesome,
2.1.
thank you. So that's 2.1 seconds, and since x equals t, that is exactly where, thank you. So that's 2.1 meters right there, because that's actually position is on that axis, which happens to sync up perfectly with time. So that's great. So we tossed something. To figure out the angle this was tossed at, we need the velocity vector at the initial position. But we're going to find the velocity vector at every stage of the way. So to find that velocity vector, I just take the derivative. Derivative of t is 1. Notice the velocity has a constant component of 1 in the positive direction. That means this thing keeps chugging along at a constant velocity in this component. Now the vertical component will change, and the vertical component is going to be negative 9.8t plus 8. Let's go ahead and get the acceleration, which hopefully should be like, oh, that makes sense. Why does that make sense, Alexander?
9.8, it's like gravity, and it's in the y direction, negative going down.
Yeah. Acceleration of gravity, right? We got negative 9.8 meters per second squared. Things accelerate toward the Earth in that direction. So let's actually pick a particular point, like here. So the velocity vector, the velocity vector is going to be tangent. There, that's better. So there's v of t. And the acceleration is always acting downward. And it's constant, so it's always 0, negative 9.8. Always pulling down, always pulling down. So the gravitational force is not adding any acceleration in the horizontal component, solely acting down. So whatever horizontal component of velocity I set this thing off with, it will continue, assuming there's no air drag and all that kind of stuff. But it's going to continue with whatever horizontal component of velocity I started with. So let's see, what is that? And that's 1. So our initial velocity, v of 0, is 1, 8. How do I figure out what angle that is? So what if I want this theta right here? How can I find that?
Product of v of t and v of 0, maybe? Or is it of s of 0, or s of t?
So what could we make this? You got the right idea. We could just pick any horizontal vector here. I think that's what you're thinking. I think it is.
The first point, right?
Yeah.
Yeah.
So to find this vector, so we're going to take v of 0 dotted with 1, 0. That's just our horizontal vector. And all we care about is the angle here. We're not interested in the length. What's cool is this is actually a unit vector, so it won't contribute any magnitude to this workings here. So that is equal to, remember how this works? The magnitude of v times the magnitude of the other vector, which is 1, 0, times the cosine of the angle between them. So I find this dot, so I'm using this rule right here, u dot v equals mag u mag v cosine of theta, using that law. And v0 is my u, 1, 0, I guess it could have been v. 1, 0 is my other vector. But v of 0 is equal to 1, 8. So this is 1, 8 dot 1, 0. equals, magnitude of that is root 65. Oh, that sounds like a road. Isn't that some kind of, or is that a highway?
Route 66.
Route 66, shit. Well, it's close. It's close. It's close. So that's root 65. This is just length 1, and then cosine of theta. This turns into 1, I think. Did I do that right? Yeah. That's just 1, so divided by root 65, like that, equals cosine of theta. So could someone please find the arc cosine of 1 over root 68? And if you could do it in degrees, or if you get radians, we'll do the conversion, so. It should be pretty steep looking at the picture, so I don't know, I'm guessing like 77 degrees. I'm just gonna make a crazy guess.
82.
82, shit, well, thank you.
0.87.
Okay, yeah. 0.87? Oh, okay. Yeah, okay. Looks steep. Shows up steep in the math. Makes sense. So we figured out our initial angle of takeoff. Cool. What kind of time? I got lots of time. Neat. Pretty good. Any questions on any of that? Because we're going to keep going down this road. What is my what is my final speed? So what is the terminal velocity? Terminal speed, let's say speed. You'll need to find the terminal velocity vector. So what is that? Terminal speed, what is the magnitude of V when I hit the ground? Take a minute. We'll do it together. How hard does that sucker hit the ground? At least how fast? Yeah, so I got that. I want to ask you another question too. So what is let's work on these things. Terminal speed. What is the time when I reach apogee? So when do we reach apogee? And in terms of both, time and x will be the same here. So when is apogee reached? That's the right word, isn't it? I think. Yeah, I'm seeing, getting some physics slight nod over there and across the way. And shit, what was that number that you helped me with? That was 2.1? Yeah, okay, we got it. Yeah, we got it right here, 2.1 seconds. So that's gonna be magnitude of V at 2.1. It's gonna be magnitude of what? Oh, you got it, hold on a sec, yeah. It sounds like you got it figured out for me. So, has anybody got this figured out?
Yeah, I don't.
I have negative 12.58.
I got
For the dot, wait,
Just
it
for
can't be.
solving that.
But the magnitude can't be negative, right?
So let's, yeah, what is the vector first? Let's slow down. Yeah, so what is this component? Just
Negative 12.58.
That sounds, okay, that sounds right, negative 12.58, thank you, that's what you were getting at, okay,
Yeah,
gotcha,
yeah.
gotcha, cool. And then, yeah, so its downward component is pretty fast, negative 12.58 meters per second. And then this is going to be, what is that magnitude?
I got 12.619617.
Yeah.
Yeah.
Sounds good. Sounds good enough for a completely bogus thing. Yeah. And that is also just meters per second. Neat. I don't know, honestly, I don't know. That sounds fast. That sounds like if you got hit in the head with that, that would hurt. Pretty bad. How do we find the apogee?
Set the lock component of U2 to 0.
Yeah, figure out when the vertical component stops changing. Yeah, perfect. So set y component of v t to 0. So that is negative 9.8.
Oh.
8 equals 0. It sounds like you might have done that, Daniel. Is that true?
Yeah, it's 0.81 or 0.82 to round up.
Thank you. Cool. 0.82
Seconds.
seconds. And so since x of t is exactly equal to the time, this is also 0.82 meters on this axis here. If I then wanted to find how high this sucker went, I could plug in t equals 0.82 into this, but God, I don't really want to. Nobody wants to. Folks who want to do everything don't want to do that. I see you looking around the room. Folks who never say, let's not do it, they're saying don't do it. So we're not gonna do it. Bless you. Appreciate you. Does this all sound good? One thing I kind of wanted to point out, just to reiterate the relationship between the acceleration vector and the velocity vector. When this thing takes off, think about what's happening. It's at its max velocity for a moment right here. And gravity is pulling down on it, so it's actually slowing down. And you can see that in the fact that the acceleration vector is not acting in the same half of the plane as the velocity. If the acceleration was up here, then this thing would be speeding up. If it had a motor on it, or whatever you call it, on a rocket, the acceleration would be up this way. But it's constantly pulling down. Right at it, the apogee, the acceleration is completely orthogonal to the velocity. And then after that, it's actually acting in the same direction as the velocity. And so the thing is speeding up is the right word, as it hits until it hits the ground. Cool. I don't know, I just like this stuff. Not enough to be a physicist, but it's enough to talk about it in Calc 3. Let's take this problem and do one more reversal on it. Oh gosh, we better talk about tangent lines. So I'm gonna bring in 4 skill checks on Wednesday. That's a lot, like 4 to knock out. The last one is on integration of vector valued functions. I don't know if we'll have a chance to get through that today. It's pretty easy. It's what's the integral of this? It's the integral of the components. So it's just like the derivative stuff. I would recommend reading through the example in there where they give you an acceleration vector, and then they ask you to integrate that to go to velocity, and then integrate that, so integrate that to go to the position vector. It's the reverse of literally what we just did, but make sure you get it. And if you don't, we can talk about it. Just shoot me an email, give you some stuff. But the very 4th skill check is on that. It's one problem of that stuff. So again, just moving backwards through this chain. You just have to remember to add constants when you integrate, and you'll be good. Oh shit, okay, hold on, just really quick. Let's just put it up here, so just so you can get, when you look at it, you like have some kind of grounding on it, and then we'll do tangent lines and call it a day. So, I don't wanna leave you hanging like that, that's not cool. So if I have the acceleration vector that looks like this, it's a1 of t, a2 of t, a3 of t. And I want to go to the velocity vector. I'm going to take the integral of each of these components. So integrate. Does that make sense on each one of those? Exactly, 100%, yep. So this is gonna be antiderivative of a1 of t dt plus a constant. Guess what that constant is? It's the, yes, c, absolutely, and it's more specifically the initial velocity at that time, in that component. So v naught of x, and then this is integral a2, the second component, plus c. But that will be the initial velocity in the y direction. And then lastly this. V naught in the z direction. Do that again. Gosh, I'm just gonna call this V1 of t, V2 of t, V3 of t, and then when I go to position, it's going to be antiderivative of this. After I figured out that constant, because I knew the initial velocity, because it was given. So there's an example in the book. Read through that example, you're gonna be so set. And don't forget, you can use resources on Wednesday. So this is just gonna be integral of that position, that velocity vector, plus initial position in the x direction. Integral v2 of t plus initial y position. And then lastly, I'm getting so sick of just even reading this. S of 0z, I'm not gonna say anything. One example like that, pretty chill. That is literally the only time we'll ever integrate a vector valued function like this. It's more gonna be, when we do integrals, it's gonna be more like integral, as you requested. But we got a ways. All right, last thing, let's talk about tangent line equations. And if I just kind of give you this, you're definitely gonna be asked on one of them to find the equation of a tangent line to a curve. We've done so much more than that already today. This is pretty chill. You just need to have this formula at your side. This is that same damn rag that I took home, brought it back. It doesn't look like they washed them. So who knows how old that rag
When you had a
is.
home with you, why didn't you wash it up?
That's a good question.
You should just throw it away and buy a new one.
Maybe so. I think that's a good idea. We do that. But you know what? I'm sick of supplying stuff around here.
If you keep a pack of microfibers, which they're pretty cheap, then you don't gotta share them with anybody. And then
You think microfiber would
microfiber's like the best one
Okay.
to do it with.
All right.
yeah.
Okay, that's a good idea. I'll just get one. And then you say I don't have to share it, huh?
Well,
All right,
other than
well
me,
then.
of course.
Well then. Okay, so good old space curve. Whee! Have fun, have a space curve. There's the R of t. Give it some dimensionality by drawing some axes in the back that it passes over. Wow. Unreal. Kind of, not really. So I've got this space curve. I want to approximate it with a tangent line at some particular t naught value. So this is r at t naught. Right there. What we're gonna do is we're going to find the tangent vector at that point. So step one, let's see, so to find the equation of a tangent line to r of t at t naught. Step one is find the velocity vector at t naught. That's going to give me a vector. I've got the point. This is the point. So remember how lines worked? We had a point plus t times the direction vector of the line. Same thing. You know how to do this. Now you just got a function to get the point and get the v. You got this. You've done this. Get your point. P naught is this. V is this guy. 2, right. But we're gonna actually make it a little. Am I gonna make it a little different? Let me see. I got something weird here. Oh, that's a T naught. Yeah. So this is slightly, subtly different, but it'll work the same. I'll show you what I mean by it's subtly different. So write L. This is going to be a vector valued line function of t equals the point of contact plus t minus t naught of r prime at t naught. Now notice the difference here with this versus that. Let's just think, bless you. Just don't write this down, but what if I had used this formula and just said this? What's the difference? What does it do? What are you saying, Kayla? Not sure, or you were saying something?
Wouldn't that, like, it doesn't have a T, well, I guess it does have a T, but never mind.
That's okay, yeah, that's all right. Does have a T.
It's not the slope of it.
Yeah, it's still slow. What is the value of this thing at T naught? L, what is this thing? If I plug in T naught here, what do I get out? R of T naught, right? So this thing here agrees with this thing at T naught. Let's just make a little note that this form here, this L at T naught, actually equals the point of tangency. But this form doesn't at T naught. What T value do I need here to be at the point of tangency?
T minus T.
Too fancy. This guy here. What T value just gives me R of T naught out? 0. So for this one here, we have equal to the point of tangency when T equals 0. So this is totally cool. It just depends on when you're thinking of time starting. So if I'm thinking of this situation here, and I want, this is the dawn of time right now. The moment I leave this curve, we're leaving our mothership, we're flying away, all time begins now. I would use this form. If I'm wanting this to be a model of this R of T, this is the way to go. And I honestly just probably go this way and you'll be okay. So write that down, use that form. Times 307. I owe you 10 minutes, right, or something. I owe you some time. I think I owe you time. Yeah. Does this make sense? Okay, so I haven't put it live yet, but I'm creating a web work to practice this stuff, this vector valued function stuff. I'm not on campus tomorrow, but if you need to talk, let me know. Or send me an email question. You'll find that I get back to you pretty promptly with email questions. But that's all I got for you. This will be the fine. So what's the skill checks? We're gonna have cross product. We're going to have, what's on there? We're doing cross product, vector valued functions. Oh, yeah, and then, yeah, I got it. So it's that, because I know there's 4 things. And then derivatives of vector value functions. And then that last one are integrals of vector valued functions. In this one, I'll give you an acceleration vector. You find the position vector. In this one, I'll probably give you a position vector. You will find tangent lines and shit like that to it. Maybe some velocities, maybe some accelerations. This will just be very basic stuff about it, and then just like basic facts, and then this will be cross product basics. Sound okay? All right, cool. And again, no stress, right? Things go bad, things go south, we do it again, no big deal. If you can't make it to my office hours and you need to make up something, I'll hook you up with a professor who can give you the skill checks. So don't feel limited by my office hours.
So for questions like that, like, just because you're not gonna be the one covering, what am I supposed to be, what are the resources I can use?
Anything except ChatGPT, and I don't think you'd use that.
Like including the internet?
Sure,
Okay.
use the internet.
Is that communicated with?
I'll communicate with him. I'll make sure he knows. He's, first off, he's not gonna be watching you at all. Not that that's like, not I'm telling, that's not like, it sounds like I'm asking you to be skeezy, but.
No, I know, I just don't want him to be like, wait a minute, are you Googling this? Like,
You can Google it. You can Google shit. You just can't Google ChatGPT. How do I do?
well, you know, it's likely to be wrong anyway, sometimes, most of the time.
Yeah. Oh, thank you. Thank you, sir. Aren't you glad we like canceled class Wednesday morning?
That does feel good.
It feels so good. I felt so good when I decided on it. Bye, Kayla.
Bye, Vicky.
I'm not gonna lie though, I felt like this morning's class, I was like on fire, like could
Yeah?
not be stopped. Yeah.
Oh
my
man,
God,
that's
that
so
was, like,
killer.
As
Oh.
far as like just real analysis goes in general, like that was probably one of my better classes.
And
that I've had
understanding,
so
you
far.
were, like,
Oh my
there.
God, like and I think it was because I had spent like, I'm not gonna lie, like I spent a long time trying to figure out those proofs, and I was
Man.
like, you know what, I've like kind of fallacy of sunk costs. Like I was like, I've done it, so I'm gonna do it. I was like, I'm just gonna get this.
So good.
And like genuinely, like sitting there today, I was like, wow, this is really.
So you're saying you're
paying off.
disappointed we're not having class?
No.
Okay.
I'm just saying that like
No.
I-
That's a
I
lot
don't-
of no's.
that was like today felt really good though.
Oh.
Like it was
That is
felt
so,
like I was
man.
on fire.
Man, do I love hearing that, Christian.
Yeah.
Oh, I'm so proud of you, man. For putting
Appreciate
the work.
it.
I mean, I always knew.
Granted, like I don't know if it's gonna be right, but whatever I like, just the amount that I was at least like looking at and trying to work my way around
Yeah.
that like the different
You know,
formulas.
it's hard for
Just like the familiarity that I feel like I have now as compared to like a couple days ago is huge. But,
Yes.
Yeah.
I'm allowed to.
Feeling
That's
good.
cool.
And he's
That's
like,
awesome,
"Are you
because
using it?"
like honestly,
Tell him.
these, if you're getting this,
Or, let him know.
you're getting it.
Yeah.
Because you're gonna see the same stuff.
That's kind of what I figured, and like as far as like building blocks go, I kind of figured like you'd be doing like foundational stuff first and foremost, and then building on top of that with like that stuff.
So proud of you, man.
Appreciate it.
Awesome.
Yeah, I'm excited to see what you think of the proofs.
Yeah, me too. Oh, is that what I got there?
Yeah,
Oh, cool.
yeah.
Awesome.
All right.
Thanks. All right.